This is the first video over chapter 11 and 13 over intermolecular forces. I'm going to take a look at the first question that we actually began with in class. I'll take a look all the way down here on page 4. Let's take a quick look at this question right here. So the question asks us, we're given 3 compounds. I'll just review intermolecular forces on these 3 compounds: acetylene, 1-propanol, and butane. Oops. And they're giving us the structures of the molecules themselves. Remember, there are 3 intermolecular forces. We have London dispersion, we have dipole-dipole, and we have hydrogen bonding. And the idea here is London dispersion operates in nonpolar molecules. This here, butane, is a nonpolar molecule. And dispersion forces, then the bigger the molecule, the stronger the dispersion forces. So this actually molecule isn't very big. Butane turns out to be a gas, as you may know, even though it's using butane lighters under pressure to remain a liquid. All right, 1-propanol versus acetone. Acetone is polar, so because it's polar, and it's polar because it's asymmetric, because you have an oxygen on top. This would be a polar molecule. And 1-propanol has hydrogen bonding. So polar molecules will have dipole-dipole forces. Hydrogen bonding will be present in 3 possibilities. You can have a fluorine, or you can also have a nitrogen. Fluorine turns out to be the strongest because it's the most electronegative. Then oxygen, and then nitrogen is the 3rd most electronegative element on the periodic table. And the reason, again, why hydrogen bonding exists in these 3 cases is because these elements' extra high electronegativity pulls the electron off of the hydrogen, exposing the positive charge, creating a very, very positive charge in these cases. Now, it should be said that 1-propanol will actually have all 3 of these forces operational. London dispersion applies to every molecule. If you have electrons, you've got London dispersion. Because 1-propanol is also polar, because it's asymmetric, because you have an oxygen on the right side, also has dipole-dipole. So butane only has London dispersion. Acetone has London dispersion and dipole-dipole. And propanol has all of the forces available. Now, these forces then influence physical properties, not chemical, but physical properties. So the question asks us, which is a list of the compounds in order of increasing boiling points? We should say that the highest boiling point will be propanol because it has the highest or the strongest intermolecular forces. The lowest boiling point would be butane. It has the least intermolecular forces. Now notice they give us the same molar mass, and that's because dispersion forces will be, as we'll see in a minute, dependent on the size, which is the mass, of the molecule. So let's come back up to page 1, and let me actually take a look at some of these questions here. So, if you take a look, I guess a quick look at number 1, it asks us, or number 2 rather, asks us, based on the data in the table on the left, which of the following liquid substances has the weakest intermolecular forces. So the table gives us vapor pressure. Now vapor pressure essentially is how quickly a substance evaporates. Notice the substance with the highest vapor pressure is this guy here, CH3OH. Highest vapor pressure means that above the liquid phase, the molecules evaporate very, very quickly. And if you were to close the container, it would give you the highest pressure. It's a gaseous version of the liquid that gives the highest pressure, which means the liquid has the weakest forces. Now this may be sounding confusing because we have OH here, so it looks like we have hydrogen bonding, so it looks like it shouldn't be the answer. Hydrogen bonding gives you strong intermolecular forces, does it not? Yes, it does. However, CH3OH is a tiny molecule. It's a very, very small molecule. It is a liquid, but it's a low boiling liquid, you can say, easy to vaporize. So you would still pick CH3OH, even though it has hydrogen bonding, because of the physical property. And here they're not telling us, but here you can see that the sizes of the molecules have actually a big, big effect. Right. So if you take a look at a similar question right down below, number 5. So number 5, for example, says, consider the molecules represented above and in the table below. So here we have nonane, here we have 2,3,4-trifluoropentane. Notice their boiling points are significantly different. Nonane has a higher boiling point. Now you notice right away that nonane is nonpolar, which means the only forces operational are London dispersion. This guy here, 2,3,4-trifluoropentane, is polar, so you have dipole-dipole forces. Incidentally, you do not have hydrogen bonding. Be careful, you don't have hydrogen bonding because fluorine is not attached directly to a hydrogen. it has to be on a hydrogen to exhibit hydrogen bonding, so the fluorine can pull hydrogen's electrons away, exposing its nucleus. So no hydrogen bonding here. You have dipole-dipole. You also have London dispersion forces. But turns out nonane wins in the overall forces because it's so much longer. It being longer actually overpowers this guy being polar. So the question is going to ask, here they are, they have almost identical molar masses. Now notice they have identical molar masses because fluorine is heavier, essentially, than carbon. That makes up some of the molar masses. But nonane has a significantly high boiling point. And this is because nonane is longer, and so the dispersion forces are greater. The longer the molecule, the more dispersed the electrons can be. So you can disperse them more on the left side, less on the right side, creating more of a negative, more of a positive partial charge. And that's the idea. So C would be the best answer. If you read through the possible answers, the carbon chains are longer in nonane than they are in the fluoropentane compound. Right. So take a look at something on the second page. We may skip this one, but you may recall the heating curve. Number 7 says liquid naphthalene at 95 degrees Celsius is cooled to 30, so we're beginning at 95. This is a liquid. So right here, what you're seeing in C, you're seeing the liquid to solid interchange. Remember, a standard heating curve that shows all 5 parts will look like this. A standard, this is a cooling curve, I'm sorry. A standard heating curve that has all 5 parts will look like this. So here they're signaling out just this portion of this cooling curve. Notice you actually have a supercooling event right here happening at B. But if you want to get the melting point, you can actually determine the melting point of the substance. Looks like the melting point is about 84 degrees C, is the melting point of naphthalene. So go ahead and take a look at the question and try to answer the question as it comes down. Let's take a look at page 3. And page 3 asks us a few interesting questions. Ooh, a little trouble there. All right. Take a look at number 13. Go slow. Okay, 13 asks us, gases generated in a chemical reaction are sometimes collected by the displacement of water as shown above. All right. It's not shown above. Well, we've talked about displacement of water before. Which of the following gases can quantitatively be collected by this method? So it turns out what we want is we want to match up waters. Water, we know, is hydrogen bonding, which means it has all 3 forces. So whichever gas we try to collect that matches water's intermolecular forces, water will dissolve. You won't be able to collect it, or you'll lose a bunch of it. So as you're collecting the gas, essentially, the water that's collecting the gas will actually keep a bunch of the gas. So we're looking for a nonpolar substance. NH3 definitely can't be collected because it's hydrogen bonding as well. This will dissolve right into water. You can create a very, very concentrated solution of NH3 in water. SO2, if you take a look, SO2 is actually polar. If you were to draw its Lewis structure, you would have to do that here or memorize its structure. It is polar. So if it's polar, it'll also dissolve. HCl, you can see right away, is polar. It'll dissolve. CO2 is nonpolar. H2 is nonpolar. Now CO2 looks like this. Now if you had to guess which one would be less polar or less, both of them are nonpolar, you would probably go for H2. H2 is a smaller molecule, a tiny molecule. Not much of it dissolves in water at all. Turns out that a little bit of CO2 can dissolve in water. Even though it's nonpolar, its dispersion forces actually allow it to slightly disperse to one side and create slightly positive and negative poles and dissolve in water. It has a low solubility, but a much higher solubility than H2 or oxygen even or nitrogen even, due to the fact that it's a bigger molecule. So nonpolar molecules could be soluble in water. And their degree of solubility depends on their size. Take a look at number 14. Let's take a look at 14. 14 says, which of the following substances has the greatest solubility in this compound here? Now, anytime you see on the AP exam or anywhere else a molecule that looks like this, we just saw a few, C5H12, considered to be nonpolar. In fact, you have 5 carbons technically in a line surrounded by all possible hydrogens. This is an organic molecule. Those of you that took organic chem have the advantage here. So because you have yourself a hydrogen on every carbon, so you double that. 1, 2, 3, 4, you get 10, then 11, 12. That's how you get it. So nonpolar, that's the whole point. Watch for these. These are all nonpolar. So which will be dissolved? NH3, just saw up here, has hydrogen bonding out. Water, hydrogen bonding out. Sodium chloride is actually a salt. Now salts, it should be said, salts are usually very soluble in water. Why are they soluble in water? Because water is very polar, hydrogen bonding, and salt is permanently has a positive and a negative. A salt has a positive, permanent negative charge. Water comes the closest to being so positive and so negative due to the fact that it has very strong hydrogen bonding forces. Now, these are not full positives. Usually we do a little delta, which means partial positive, partial negatives. All molecules have partial positives, partial negatives. Salts have full partial, full negatives. Salt will actually be very soluble in water. That's a good thing to remember. So in this case, it's out. SiO2 kind of looks like it's salt type as well. It turns out to be, as we'll see in a minute, not salt, but it also looks ionic, so it's out. In fact, CCl4 is nonpolar. You got a carbon, you have 4 chlorines. All right. So this will actually be the one that's nonpolar, the one that will be soluble. Let me take a look. Let's take a look at a question on page. On the last page, just maybe a few comments about some equations. Let's take a look at this page right here. Here we have number 20 is actually a strange lab type question. See if you can think through it. And I was going to just quickly take a look at 22 and 23. Now it's rare that they'll ask about these type of calculations, but this is kind of a review of two things. Number 22 is a review of percent by mass, and 23 is a review of mole fraction. We actually took a look at mole fraction, which was X. Percent by mass, so if a compound is 50% by mass H2O, or H2SO4, sulfuric, you can say that there is 50 grams of H2SO4 in 100 grams total. Which means if you were to do some calculations, you have a solution that's 50 grams water and 50 grams H2SO4. Now, they tell you, anytime they tell you the density, here's the density of the solution, then you can actually convert from grams of water into milliliters, because they give you grams per milliliter. You can find out milliliters. And then if you want to know the molarity, you can take that to liters. Molarity, remember, is moles over liter. And the moles, to get moles, you would have to convert grams into moles. So that's how you convert from, say, percent mass, kind of take apart what the percent mass idea means, and then try to get it to moles, try to get it to liters, and do moles over liters. This one, the calculations turned out to be very tricky, and I don't know if this was from an actual AP exam or just pulled away. The calculations look a bit tricky. Go ahead and use a calculator for this, just so you can practice. 23 says we have methanol in water by mixing together some methanol and some water. So we want the mole fraction. Mole fraction is moles, in this case of methanol, CH3OH, over total moles. And this should be easy enough. This one you can probably do without a calculator. Try it. You have to convert this into moles by dividing by molar mass of methanol. Actually, they don't give you the molar mass of methanol. This may be, but the numbers are clean, so it sounds like possibly you can do this without a calculator. Try it. Get the molar mass of methanol, divide. Molar mass of water is 18, divide, and try to solve this problem and find what the answer is. All right, so we will, if you want, we can do this one of these in class. Until then.